Hello. So, um, this is my second recording, my second video, and today and right now I'll be discussing homework 3.1 because I received multiple questions. It has been discussed through the TA hours, but this is a follow-up. For the first part, initially you're asked to describe impedance matching. I think there are lots of resources in this, but feel free to ask me if you don't get the concepts. We can discuss it during the TA hours. But what I want to focus on right now is reproducing the figures with the necessary description of those results in figure 8.14. So let's open the figures. Let's start by developing this circuit. So currently I have LT Spice open. You should be familiar right now with the software. You just press File, New Schematics, and save it at your local folder. Save as, let's call it, this is homework 3. Let's call it at homework 3.1 B dot ASC. We start by developing the circuit. You can input the elements from top. You can pick your inductor, resistor, or capacitor, or you can use the shortcuts. So for a resistor, you can just press R, L for an inductor, L, control R to rotate, and C for a capacitor. W for wires, or F3, depending on the version of LT Spice you're using. It's a very straightforward process. You and escape to deselect. Hopefully everybody is familiar with this right now. All right. Currently, I want to input the values, but I want to input them in foot as they are uh, written here. So I will define some parameters. To input a command, you just press dot, or you can go for edit, spice directive. As you can see, the shortcut is dot. So we'll input a command called params, and we'll name some variables. So we'll name our L1, which is the inductance for our inductor, is 97.5 nano times foot. Our C1, which is 39 pico times foot. Our R1, which is 50 ohms. Press OK. Let's input another parameter. So I'm pressing dot on my keyboard. Dot params foot is equal to 3, which is given here. Let's enlarge our circuit a bit. Like we don't need this. Right. So to define those elements as parameters, you just select them using curly brackets, name it as R1. For the capacitance, use curly brackets, name it as C1. All right, so this is the name of the element. So you have to select the value, name the value as C1. And for the value of the inductance, call it L1. Right now, we need to plot a Z equivalent. So Z equivalent, I'm not sure, can I, yeah, I think I can annotate through Zoom. So Z equivalent is the Z looking through the circuit. So how can we plot this? We should know that Z is equals to V over I. So if we set a source of 1, let's say I is equal to 1, so Z will be equal to V. That's like a smart trick. Let's try this out. So let's cancel all the how to annotate. Right. Let's keep it here. So let's put a volt of, let's put a current source of 1. So pressing insert component current, which is somewhere C, CUR current. Control R to rotate it. And you can just put a wire. Right. In our example, I don't think they mentioned an omega, a frequency that's the current is operating at. So we can just uh, input any value. Let's make it, so we press advanced, and since it's an AC circuit, let's make it 10 with a phase of 0. And we can pick, we don't need, so this part is for transient simulation, and this part is for AC simulation. So you just change the values here, press OK. Let's cancel the annotation. Clear, clear all. All right. So are we missing anything? Yes, we are missing the simulation. What kind of simulation are we gonna do? We'll probably do an AC simulation. So let's start by pressing dot or pressing simulate, configure analysis, or you can use the shortcut A. Choose AC simulation, type of sweep. I think it's mentioned in the notes, it's decade, or probably not mentioned. Yeah, I think it's decade with a start frequency of number of points per decade 200, start frequency 2.72 mega MEG, and stop frequency is 27.2 MEG. One mistake I did during some previous TAs is that instead of MEG, we wrote M, which gave us the value in milli, and the results were wrong. Took us some time to figure this out, so be careful. For mega, it's MEG. Everything should be all right. Yeah, everything should be all right. Let's put the AC simulation here, and we can run. We can use Alt R as well as a shortcut. The circuit doesn't have a ground. Yeah, I forgot the ground. Press G for ground. Just place your ground, run. Yeah, or try to have another circuit. Let's close it. Let's close it. Save. No, we do not need to save it. So this is my result. We can mess around with the displays. I think this display looks better. To change it from black to white, to change the colors of the result, we can just use waveform settings, and should be somewhere here. Color schemes. You can mess around to change your colors, make it look presentable. You can also change the colors in your schematics and have fun. You can also insert a grid, but I don't think it will show unless we plot something. So right now we are plotting the ZEQ, or the equivalent Z of all of this part. We mentioned that ZEQ is the current I over the resistance, over the voltage over the current, which is the voltage. So as you can see, we have the voltage here, and in real and imaginary. Let's see if it looks like the results presented in the lecture notes. And it does, except here they have the values in volt, and while we have them in dB. So let's change the scale. So to have the values in volt, we can just use linear 500 volts. And let's see if it's the same. Is it 50 volt? 50. And so there's something wrong in the scale. All right, and as well as it's not in volts, it's in ohms. So if you want to change it to ohms, we can try something out. We can plot the current. So plot I1, or plot I1. So this is I1, and we can, using the right click on V1 and just change its notation. So we want to plot V1 over IL1. We know the notation of IL1 from here. Press OK. Delete. So I press delete and delete. I press delete and delete I1. So right now it's in ohms. Everything makes sense. Let's check the values for. Let's check the values. And let's turn on the grid to make it look better. At right, I'll zoom to fit view grid, right? And right, we have a cursor. So we want to see the value using the cursor. We can go for this value here and see what value it is. Compare it to the value we had in the lecture notes. Where is the lecture notes? Right, so it's 35, 30 megahertz. At 30 megahertz, somewhere over here, it's 35. So yeah, so the values match. Everything should be all right. The second part, yeah, so the magnitude and phase, you can calculate the magnitude and phase, or you can also convert it to rectangular notation. You can do this manually or through piece pies. Note you can also plot the rectangular form in piece pies. So yeah, so this part is fine. Another question. Right. So this is for your homework. I received multiple questions for this problem. Let's say regarding the matching part, let's say you want to match the circuit. How can we do this? How can we match it? So first, let's start by thinking about it. What's matching? Matching is when the maximum power reaches the resistance. This is one definition, reaches the load. This is one definition of matching. And what is the maximum power? So it's a bit tricky here because the maximum power, let's stop first. Let's stop for this part and go for another video for matching. Recording, stop.